Today you will be identifying and classifying polynomials. We'll start off with defining a monomial or monomial. This is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. Okay, so an example of something like this would be like 2x or negative 3x to the fourth, right? So we have a real number, a variable, or a product of a real number and one or more variables with whole number exponents. A polynomial is a monomial or sum of monomials. Okay, so when I have several monomials and they are separated by addition, we call that a polynomial. The degree is the greatest exponent among the monomial terms. In the polynomial function, a polynomial with variable x defines a polynomial function of x. So if we look in the box, when we talk about the standard form of a polynomial arranges the terms by degree in descending order. A polynomial function p of x in standard form is as follows. Now this form looks really confusing, but all you have to recognize that this a sub n x to the nth power, that just means your first term, where a sub n is your leading coefficient and the n is the degree. So that's just the largest exponent. And notice as you move through the polynomial, the degree goes down by 1 until you get to the constant. Okay, so a sub 0 or a naught is the constant or a number without the variable. If we look at our sample example, the polynomial p of x equals 2x cubed minus 4x squared plus 3x minus 1, the cubic term is 2x cubed because the x is to the third power. The quadratic form is negative 4x squared. The linear term is positive 3x, and the constant term is negative 1. Now, as we look through the degrees, if I have a degree of 3, we call that a cubic. There's an example, and because there's two terms, that is a binomial. Notice if we have a degree of 4, we call that a quartic. Notice we have an example. There are 3 terms. We have a trinomial. Once you get past 3 terms, we just call it a polynomial. Other degrees, you might see quintic. That would be a degree of 5. You might see a degree of 1. That would be a linear term, and etc. So if we look at our first type of problem, we're going to write each polynomial in standard form and then classify it by degree and by the number of terms. So in this first example, our largest exponent is negative 5x cubed. So I'm going to write that first. The next descending power is 4x squared. The linear power is negative 6x, and then plus 1. Now, if we were to classify this, what would we classify this by degree? Well, remember, we've written it in standard form, so we're looking at this leading degree here, and we're going to call this a cubic. And now we have to classify it by the number of terms. Notice we have 1, 2, 3, 4 terms, so this is a polynomial. And that's all you got to do. If we look at this next example, and what is our largest exponent? Well, we just have a linear and a constant, so our standard form is still 4x minus 5. And if we were to classify this by degree, if I have 4x, that's the only thing that has an exponent, we're going to call this a linear. And then 2 terms we call a binomial. Much like if I'm riding a bicycle, right? It's got 2 wheels. Now try the 2 example U-tries. Hopefully you found the first example you try to be in standard form, 5x to the 4th plus 3x cubed minus x, and it is a quartic trinomial. And the one on the right, the standard form is negative 2x squared plus 10x plus 3, and that is a quadratic trinomial. So now we're looking at turning points and behavior. So turning points, these are places where the graph changes direction. For example, in this picture on the left, we go down and then we turn around and go up. That would be a turning point. And as we continue, we go up, then we go down, a second turning point, and then we go down, then we go up, a third turning point. Notice the picture in the second to the left has one turning point. So does this one, it doesn't really have any turning point. And then notice this one, we have one turning point, two turning points, okay? Now, end behavior, these are the directions of the graph to the far left and to far right. So for example, I have the end behavior up and up if my leading coefficient is positive and the degree is even. That means our graph rises to the right and to the left. So notice we have x to the fourth. If my degree is even and the leading coefficient is positive, we can say up left, up right. We can say rises left, rises right. Or for those of you taking calculus, you can say that the x left behavior, which would be negative infinity, as x approaches negative infinity, then y, or f of x, approaches positive infinity, right? Because my left end behavior is going up. I can also say as x approaches positive infinity, which would mean as x increases, then my y values, f of x, approaches positive infinity, because on the far right, our graph is also going up. We have, if the leading coefficient is negative and the degree is even, the graph falls left and right. Notice we have negative x squared. So even degree, negative leading coefficient, we can say down left, down right. We can say falls left and right. Or for those of you planning to take calculus, as x approaches negative infinity, then f of x also approaches negative infinity. So that means from the left, it falls. As x approaches positive infinity, f of x approaches negative infinity, meaning as x increases, y is going down, okay? If we look at the next picture, the leading coefficient is positive and the degree is odd, the graph falls left and rises right. Okay, so if it is odd and positive, it is down to the left, up to the right. If we wanted to put this in our other notation as x decreases, then y, or f of x, also decreases because far left-hand behavior goes down. As x increases, meaning as x gets larger, our y values, f of x, is also getting larger because our far right-hand behavior is going up. And then if we look at the next one, if my leading coefficient is negative and the degree is odd, so I have a negative leading coefficient, negative degree, our graph goes up left and falls right. Or I can use our fancy notation as x goes to negative infinity, f of x, or y, goes to positive infinity because on our far left behavior the graph is up. As x goes to infinity, meaning it's increasing, our y value goes to negative infinity, meaning the far right behavior is going down. Okay, a trick that I always remember, if it is even, the end behavior is going to be the same, meaning either up, up, or down, down. And if the degree is odd, the end behavior is going to be opposite, either up, down, or down, up. So notice in our next example, we're going to describe the end behavior left and right hand of the graph of each function, and we're just going to get going. The first thing I would do is I would look at the degree. I notice my degree is an even number and our leading coefficient is positive. So that tells me we're going to have the same behavior. Remember, if it is even and positive, then we have up left, up right. Or we can say as x approaches negative infinity, meaning as x is negative, y goes to positive infinity. And as x is increasing, y is also increasing. If we look at this next example, notice we have an e odd degree again. This time my leading coefficient is negative. So if it is odd, then that means we're going to have opposite end behaviors. And if it is a negative, that means we are going to go up to the left and go down to the right. Okay, let's use our fancy notation. As x goes to negative infinity, meaning as x gets smaller, our y value is going to positive infinity. As x goes to infinity, meaning our right-hand behavior, f of x is going to negative infinity. And that's it. That's all you got to do. I want you to now take a minute and try the example you tries. Okay, so hopefully you found for the first example you try, you have going down to the left and up to the right. Okay, notice your leading coefficient is even with an odd, or positive with an odd degree. So that means we're going to go down to the left and up to the right. Notice your left-hand behavior. X approaches negative infinity, y is going to negative infinity. And as x approaches positive infinity, y is going to positive infinity. For the other example, you should have down to the left and down to the right. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches negative infinity. And that's it. That's all you got to do. Okay, so now we're looking at turning points again. So the graph of a polynomial function of degree n, where n is at least 1, has at most n minus 1 turning points. Okay? Other tricks. The graph of a polynomial function of odd degree has an even number of turning points. The graph of a polynomial function of even degree has an odd number of turning points. Okay, so let's look at what this illustrate this. So in the line, which has a degree of 1, notice there's no turning points, meaning where we go from a positive to a negative direction. However, once we look at a degree of 2 or a parabola, notice we have only one turning point, which would be an odd number of turning points. If we look at the first third degree, notice we have 0 turning points. And then the other third degree, we have 1, 2 turning points. So if we have a degree of 3, we either have 2 or no turning points. So suppose we have a set of polynomial outputs. You know their inputs are an ordered set of x values, which consecutive x values differ by a constant. We can analyze the differences of consecutive y values to determine the least degree of the polynomial function. If the first differences are constant, the function is linear. If the second differences are constant but not the first, the function is quadratic. And if the third differences but not the second are constant, the function is cubic, and so on. So if we see a problem where it says, what is the degree of the polynomial function that generates the data as shown? It's actually pretty simple. All we're going to do is we're going to just do some basic subtracting. So if I take negative 1 minus 7, minus negative 7, which in turn is positive 6. If I take negative 7 and subtract negative 3, we do get negative 4. If I take negative 3 minus 5, that's negative 8. 5 minus 11 is negative 6. 11 minus 9 is 2. And 9 minus a negative 7 is 16. Now, do all these numbers match? No. They don't. So guess what? We get to do it again. 6 minus a negative 4 is 10. Negative 4 minus negative 8 is 4. Negative 8 minus negative 6 is negative 2. Negative 6 minus 2 is negative 8. And 2 minus 16 is negative 14. Now, did we get the same number? Nope. Guess what? We're going to do it again. Okay, so 10 take away 4, 6. 4 minus negative 2, 6. Negative 2 minus negative 8, 6. Negative 8 minus negative 14, 6. So we notice how these all match. And if we are above box stated that if that first set of differences, this would be a linear association, but they didn't match. Then the second one would be the next degree quadratic. Okay, now did it match? The answer to that is no, it didn't match. And the next one, the third differences would be like a degree of 3 cubic. Did we have the same differences? Yes, so it is a cubic function. Now I want you to take a minute and try the next example you try. Hopefully for this example, you found the difference to be 24 and the degree to be a quartic. Because remember, we have 1, 2, 3, 4 steps until we have a same constant, meaning we have a 4th degree polynomial.